This conference will now be recorded.
Yeah, dear students, in the last session, we have discussed about joint moments. So actually, we find the joint moments to find the statistical characteristics or the statistical parameters of multiple random variables, right? So in the statistical parameters, we have targeted one parameter mostly in the last session, that is covariance. So in the last session, we have discussed about what is covariance and how to define the covariance and the properties of covariance. And these are the things which we have discussed in the last class. And at the same time, we have discussed about conditional expectation and conditional moments, right? So here conditional expectation and conditional moments. So in the last class, we have also done some problems related to conditional expectation and conditional moments. So usually the conditional moments can be derived by using conditional density functions, right? So therefore, first we are supposed to find the conditional density functions by using which we can find the conditional moments, in which that may be conditional mean value or conditional variance value, right? So in the last class, we have done some problems related to these statistical parameters calculations, right? So now let us start this session with a problem related to the statistical parameter, that is covariance, right? So here we can also use this as a property of covariance, and sometimes in the exams you can expect the property as a problem, the proof of the property as a problem, and that is why I'm just taking the problem like this. If at all, if x and y are two random variables, then prove that the covariance of x plus a y plus b is covariance of x plus a y plus b equal to the covariance of x y itself. That is, even if you add a constant values to the random variables, the covariance does not vary. That is what the property we have, and we are supposed to prove this if a comma b are constants, right? So now, how to solve this problem? We know the formula for covariance. What is the formula for covariance? Yes, if at all, if I take the covariance of x comma y, that is nothing but expectation of x minus x bar into y minus y bar, right? So the same same formula I am taking here. That is, if at all, if x comma y are two random variables, then how can I write a covariance of x plus a comma y plus b? Instead of x and y, we should write x plus a and y plus b. Therefore, the formula becomes expectation of x plus a minus x plus a bar into y plus b minus y plus b bar. Bar means nothing but expectation, right? So here, therefore, if I rearrange the terms, how can I write this one? X plus a minus x plus a whole bar, in the sense nothing but expectation of x plus a. If I take expectation of x plus a as per the property of expectation, it becomes expectation of x minus expectation of a. Anyway, constant expectation of constant is again the constant itself. Therefore, the resultant will be minus x bar minus a into here y plus b minus y bar minus b. Here the two constants gets cancelled, and we get the resultant as expectation of x minus x bar into y minus y bar. It is nothing but the formula for covariance. So this is the way to solve the problem and prove the relation, right? Simple problem. So let us take one more property as a problem. Let us try it, right? So here, what is the property? if x comma y and z are three random variables, then prove that covariance of x plus y comma z equal to covariance of x comma z plus covariance of y plus z. So sometimes we can take this as a property, and sometimes you can consider this, you can expect this as a problem in the examination, right? So you are supposed to prove this relation. If at all, if x comma y comma z are any three random variables, you can write the covariance of x plus y comma z equal to covariance of x comma z plus covariance of y comma z, right? How do you prove this? First, let us take the formula. As per the formula of covariance, covariance of x plus y comma z equal to, so here how do you write the formula? In the place of x we have x plus y, therefore I am substituting x plus y in the place of x here. That is expectation of x plus y minus x plus y bar into z minus z bar, right? Expectation of x minus x bar plus y minus y bar into z minus z bar, right? So here what is going to happen here, if I expand this expression, expectation of x minus x bar into z minus z bar plus expectation of y minus y bar into z minus z bar, right? So as a result, what is this first one? It is nothing but expectation of x minus x bar into z minus z bar is covariance of x comma z. Similarly here, expectation of y minus y bar into z minus z bar is covariance of y comma z. So therefore here we are able to prove this relation, right?
This conference will now be recorded.
Yeah, right. So this is the way to solve the problem or to prove the property, right? So now we are moving to the next topic. So what is the next topic? Joint characteristic function. So far what we have discussed about operations on multiple random variables. So in the operations on multiple random variables, we have seen how to calculate the statistical parameter values by finding the joint moments, right? So now we are moving to joint characteristic function. Already we have discussed about characteristic function in the single random variable case. So what we have discussed in the case of single random variable, the characteristic function is nothing but a function which can generate moments, right? Here also we consider the joint characteristic function as a function which can generate the joint moments, right? So therefore, how do you define the joint characteristic function? Here the joint characteristic function of two random variables x and y is given by the same way which we have used to define the characteristic function for single random variable case, right? How do you write? That is phi xy of omega 1 comma omega 2. As I am taking two random variables here, I am writing x comma y here, and again the parameters, the variables will become omega 1 comma omega 2. Two variables will come into the picture, right? And it becomes the expectation of e power j omega 1 x plus j omega 2 y, right? So in the single random variable case, we used to take the formula as pi x of omega equal to expectation of e power j omega x. As we are taking two random variables here, I am writing it as expectation of e power j omega 1 x plus j omega 2 y. So in the integration form, if I write integral minus infinity to plus infinity, again integral minus infinity to plus infinity, double integration. Why? Because we have two variables here, dx dy, e power j omega 1 x plus j omega 2 y into f x comma y of x comma y. It is nothing but joint density function of the two random variables x and y, right? So it is the definition for the joint characteristic function of the two random variables x and y, right? So here what is the purpose of defining the characteristic function here? The joint characteristic function. In the single random variable case, we have discussed that the characteristic function is used to derive moments, right? And at the same time, the moments are used to define or to find the statistical parameters like statistical mean or statistical mean square value or statistical variance or statistical skew and so on, right? So here similarly we can use this joint characteristic function for finding the joint moments and using which you can find the statistical parameters like again the means of individual variables, random variables or variances, or jointly you can find covariance, right? So therefore the expression is recognized as the two-dimensional Fourier transform of joint density function. In the case of single random variables, and we called that as just Fourier transform. But here, as we have two variables, we call it as two-dimensional Fourier transform. And therefore, from the Fourier transform relation, using the Fourier transform relation, by using the expression for joint characteristic function, I can derive the joint density function. How do you write? Therefore, from the definition of inverse Fourier transform, we also have the density function representation in terms of joint characteristic function. That is, f of x comma y or fxy of x comma y equal to 1 by 2 pi whole square integral minus infinity to plus infinity double integral minus infinity to plus infinity characteristic function x comma y of omega 1 comma omega 2 into e power minus j omega 1x plus j omega 2y d omega 1 d omega 2, right? So that is the way to derive the joint density function using the joint characteristic function. If you are aware of the joint characteristic function, you can derive the joint density function, right? So this is the relation between the joint characteristic function and joint density function. Now, as I said, the main purpose of defining the joint characteristic function is to derive the moments from it, right? So here we derive the joint moments from the joint characteristic function. How do you derive? The joint moments about the origin m suffix nk can be found or can be derived from the joint characteristic function as follows. How do you take the relation? So in the single random variable case, we take m suffix n, but in the case of multiple random variable case, we take m suffix nk, and there the order of the moments will be defined by n suffix n, whereas in this case the order of the moments will be defined by two variables here, that is n and k, and we can write the definition here. And as we have already derived in the single random variable case, the definition for the moment is derived in terms of the characteristic function in the case of single random variable. Therefore, I am not giving the proof for this here, and you can derive in the similar way. The only difference here is there we have used the single differentiation with respect to omega, whereas in this case, since the function itself a function of two variables here, it is a function of two variables here, it is taking the partial differentiation with respect to two variables omega 1 and omega 2. Therefore, the definition can be taken like this: m suffix nk equal to minus j whole power n plus k into dou power n plus k pi x comma y of omega 1 omega 2 by dou omega 1 power n dou omega 2 power k, where omega 1 and omega 2 both are equal to zeros, right? So by making both the values, that is omega 1 value and omega 2 values equal to zeros, I can define or I can derive the moment m suffix nk, right? And now coming to the properties, how do you define the properties, right? So here, how do you write the properties? First property, same as your characteristic function. So that is, what is the first property in the characteristic function? That is, in the case of single random variable, always the characteristic function will have its maximum value only at omega equal to 0, right? The similar way, we have the property for joint characteristic function, that is, joint characteristic function is maximum only at omega 1 equal to 0 and omega 2 equal to 0, and the maximum value is equal to 1, right? That is pi xy of 0 comma 0 equal to 1, which is a maximum when compared with all the other values in the function pi xy of omega 1 comma omega 2, right? Now coming to the second property, if two random variables x and y are statistically independent. So when the random variables are said to be statistically independent with respect to the density function, yes, in the statistical independence, we have discussed that the two random variables are said to be statistically independent if at all if the joint density function equal to the product of two marginal density functions, that is fxy of x comma y equal to fx of x into fy of y. That is the condition for statistical independence. And if at all if any two random variables are statistically independent, then what is going to happen to the joint characteristic function? Yes, the joint characteristic function pi xy of omega 1 comma omega 2 equal to individual characteristic functions of x and y, that is pi x of omega 1 into pi y of omega 2, right? So here we can also take a proof for this. How do you take? Simple proof. Pi xy of omega 1 comma omega 2 as per the definition, expectation of e power j omega 1 x plus j omega 2 y. I am just taking here e power j omega 1 x into e power j omega 2 into y as per the property of exponential term. I am just taking the expectation into the equation. I am writing into the separator expectations as for the statistical independent random variables, the expectation follows this property, right? So therefore, expectation of e power j omega 1 x into expectation of e power j omega 2 y, and therefore you can write it as pi x of omega 1 into pi x of omega 2 as e power j, expectation of e power j omega 1 x is nothing but characteristic function of x, and similarly it is the characteristic function of y. Therefore the joint characteristic function equal to the product of individual characteristic functions if at all if the two random variables are statistically independent. Got it? This is the way to prove this. And another property we have for the joint characteristic function, that is by setting either omega 1 equal to 0 or omega 2 equal to 0 in the equation of joint characteristic function. What is going to happen if at all if any omega 1 or omega 2 equal to 0? Ultimately, one exponential term will get vanished. That is here, there is no either j omega, if omega 1 equal to 0, there is no e power j omega 1 x. If at all if omega 2 equal to 0, ultimately this exponential term is going to be vanished, and only we are going to be having only either e power j omega 1 x or e power j omega 2 x, right? If at all if any one variable, that is either omega 1 or omega 2 equal to 0, then the characteristic functions of x and y are obtained. They are called marginal characteristic functions. Marginal characteristics. So that is pi xy of omega 1 comma omega 2 equal to expectation of e power j omega 1 x plus j omega 2 y. If at all if omega 2 equal to 0, the second term will get vanished, and ultimately we are here we are left out with expectation of e power j omega 1 x, which is nothing but pi x of omega 1. Similarly here, if omega 1 equal to 0, it becomes expectation of e power j omega 2 x. It is nothing but pi x of omega 2. These two are called pi x of omega 1 and pi x of omega 2 are called joint characteristic functions. Am I clear? Next, in the two random variable case. So next topic is jointly Gaussian random variables. So here, as I said in the very first chapter, the Gaussian random variable is discussed in the very first chapter, right? As I said in the very first chapter, Gaussian random variable is going to play a major role in the electronics and communication applications, right? So here in the central limit theorem also we have discussed that if at all, if number of attempts are taken, or if the same experiment is done for n number of times, or if n number of density functions are added together, the resultant random variable is going to have, or the resultant density function is going to be Gaussian, right? So that is here the Gaussian random variable is having a, that is, the Gaussian random variable is going to play a major role. That is, the significance of Gaussian random variable is very high in the case of electronics and communication applications. Therefore, here we are going to discuss about jointly Gaussian random variables. In fact, we have discussed several random variables in the very first chapter in the single random variable case, but here we are just taking only jointly Gaussian random variable case for multiple random variables, right? So here in the first, let us consider two random variable, and then we extend the same to n random variable case. And now we are going to see how to define the joint Gaussian random variable. We have seen how to define the Gaussian random variable. The random variable is said to be Gaussian if at all if the density function is so and so. That is what we have discussed in the very first chapter. Now let us see how to say the two random variables. Let me talk x and y, right? So when I can say, or when can I say the two random variables x and y are jointly Gaussian? Yes, two random variables x and y are said to be jointly Gaussian if their joint density function is of the form. What is the density function here? Jointly Gaussian density, a very important expression here. 1 by 2 pi sigma x sigma y under root 1 minus rho square. What is rho here? Nothing but the correlation coefficient, right, of x and y. X and y. Sigma x is standard deviation of random variable x. Sigma y is standard deviation of random variable y, right? Expect exponential of minus 1 by 2 into 1 minus rho square into x minus x bar whole square by sigma x square minus 2 rho into x minus x bar into y minus y bar by sigma x sigma y plus y minus y bar whole square by sigma y square. That is, what is the sigma x square and sigma y square? Nothing but variances of random variables x and y. That is, x bar is expectation of x, that is the mean value of the random variable x, and y bar is expectation of y, that is the mean value of the random variable y. Similarly, sigma x square is expectation of x minus x bar whole square, that is variance of the random variable x. Similarly, sigma y square is expectation of y minus y bar whole square, that is variance of the random variable y. And what is rho? As I said, correlation coefficient, that is cxy by sigma x sigma y, where cxy is expectation of x minus x bar into y minus y bar, right? So that is it is a very important equation for the communication application. That is, if at all if the two random variables x and y are jointly Gaussian, then you can write the density function like this. Am I clear? Right? And yeah, for example, if I take the pictorial representation, how do you represent the Gaussian density function pictorially or graphically? So we have seen the Gaussian density function in the case of single random variable, right? and only it is two-dimensional. Why? Because the density function is along the vertical axis and the random variable x is along the horizontal axis, and therefore the density function will be like Mexican hat, like a Mexican hat, right? I mean like this. So here like this. And similarly here, if I take multiple random variables, you need to take a 3D view. That is, along the vertical direction, you will be having density function f of x comma y, and this plane will become the xy plane. Xy plane in the sense, the plane of the two random variable elements, that is x and y. X and y. That is, so here, when the random variable values changes, how the density function is changing is represented in the graphical way. And if at all if the change is like this, you can call this function as joint Gaussian density function, or we can also call bivariate Gaussian density. Bi in the sense two. Bi means two. Bivariate, as we have two random variables here, we can also call it as bivariate Gaussian density function, right? So it is the graphical way. You can realize this, you can simulate. So in the MATLAB, here, whatever the application we are discussing in the PTSP subject, and everything can be simulated using a simulation software, MATLAB. You can try it, you can derive, I mean, you can see the graphical representation of every density function which we have discussed so far. Maybe Rayleigh density function, maybe Gaussian density function, maybe exponential density function in the case of single random variables, and coming to the multiple random variables, now in this case, jointly Gaussian density function for two random variables, that is bivariate Gaussian density. So this type of picture can be seen by simulating the density function equation in the MATLAB environment. Not only MATLAB environment, you can use any type of simulation environment. I'm just giving an example, that is why, because you have the same basic simulation laboratory in this particular semester, and there you can try with the MATLAB environment. You can generate the graphical representation of Gaussian density function in the case of two random variables, and you can see this type of picture, right? And if you go into the picture, actually the picture can be understood like this. Its maximum value is located at which value, at which position? It is located at the point x bar comma y bar. This center point is called x bar comma y bar, the mean values of the two random variables. And at that point, you'll be having the maximum value. That is the hat. That hat is like this, and the hat peak value will exist at x bar comma y bar, right? And another thing you need to remember here is always the maximum value can be represented as 1 by 2 pi sigma x sigma y under root 1 minus rho square. That is fx comma y of x comma y less than or equal to fx comma y of x bar comma y bar, where the Gaussian function is maximum, and is equal to 1 by 2 pi sigma x sigma y under root 1 minus rho square. It is the magnitude of this particular function at x bar comma y bar. Am I clear? Right. So now the locus of the constant values of fx comma y of x comma y. So that is, if I take the constant values of fx comma y of x comma y, the density function, the constant values of the density function, if I take, and if I take the what you call locus, the locus of the constant values, and that locus will be in the form of an ellipse, and it is the locus of the constant values of the density function, right? You know about locus, you might have studied about the locus, right? The locus of the constant values of the density function is nothing but an ellipse, that is elliptical shape, right? The center of the ellipse can be here x bar y bar, and it is shown in the figure, right? And here the rotation angle can be calculated by using the equation, that is theta equal to 1 by 2 tan inverse. So that always the rotation angle is depending on what? Here it is depending on the variances of the two random variables and also the correlation coefficient of the two random variables, right? So that is, I can take the rotation angles in terms of the variance. So why? Because the variance will show the dispersion of the density function, right? Sigma x square will show the dispersion of density function of random variable x. Similarly, sigma y square will show the dispersion of, here this dispersion in the sense, here you can see two images. This image is one density function and this image another density function. That is two Gaussian density functions you can see. One is related to x, another one is related to y. And the dispersion of the two functions will be defined by variances sigma x square and sigma y square. Based on the variances, you can take the rotation angle, right? So theta. And here we can take a note, that is, if at all if the standard deviation or the dispersion is equal, both the functions are having the same or equal dispersion, and the correlation coefficient is 0. Correlation coefficient will become 0 when the covariance is 0. When the covariance is 0, right? So if at all if rho equal to 0, then the ellipse degenerates into circle. So now we have ellipse. If at all if both their dispersions are same and the covariance is 0 or correlation coefficient is 0, that elliptical shape becomes circle. And if at all if the correlation coefficient is either +1 or -1, the ellipse degenerates into axis rotated by plus or minus angles plus or minus pi by 4 respectively. In the sense, if it is rho equal to +1, it takes angle by plus pi by 4. If the rho equal to -1, the angle is minus pi by 4. Based on the rho value here, the rotation takes place along the axis, right? Now, if rho equal to 0, the random variables x and y are called uncorrelated. This part we have discussed in the last session. If the correlation coefficient is 0 or if the covariance equal to 0, then the two random variables are said to be uncorrelated. This is what we have discussed. So therefore, what I can write here, if I substitute rho equal to 0 in the expression of joint density function of bivariant density function or joint density function of two random variables x and y, right? So here if I substitute rho equal to 0, what is happening here? It is becoming 0. It is becoming 0, and the resultant can be taken as 1 by 2 pi sigma x sigma y into exponential of minus of x minus x bar whole square by, this is 2 sigma x square. And earlier we used to have another term in between, and that term is getting vanished here. As rho equal to 0, the whole term becomes 0. Therefore here there is no term in between these two terms, right? So here if I take the exponential term separately, and this becomes exponential of minus of y minus y bar whole square by 2 sigma y square, right? If you observe the expression, how do you write this expression? If I separate the whole equation into two terms, how do you separate? That is 1 by under root 2 pi sigma x square, and this term another part will be 1 by under root 2 pi sigma y square exponential of minus of x minus x bar whole square by 2 sigma x square. Here also exponential of minus of y minus y bar whole square by 2 sigma y square. So if you observe these two terms, are you able to recognize the two terms here? Yes, exactly. The first term is nothing but the density function or the Gaussian density function of the random variable x. Similarly, the second term is the Gaussian density function of the random variable y. So that is, here it is absolutely proved that if at all if the two random variables are uncorrelated, the density function, joint density function, is equal to the product of marginal density functions fx of x and fy of y, right? And as I said, fx of x and fy of y are marginal Gaussian density functions. That is, I can write like this: fx of x is marginal Gaussian density function of x. Fy of y is marginal Gaussian density function of y. Now, let us take a problem. Simple problem. What is the problem given? If x and y are two jointly Gaussian zero-mean random variables with variances of 1 and 4 respectively and covariance of 1, find the joint PDF fx comma y of x comma y. Read again. X and y are two jointly Gaussian zero-mean random variables. What is the mean of random variable x? 0. What is the mean of random variable y? 0. What is the variance of x? With variances of 1 and 4 respectively. In the sense, variance of x is 1, variance of y is 4. And covariance of 1 in the sense cxy equal to 1. Find the joint density function fx comma y of x comma y. How do you calculate? Yes, we know since the two random variables are jointly Gaussian, we know the expression for joint density function or jointly Gaussian density function, right? So if I substitute the given data, so what is the given data? X bar equal to y bar equal to 0. Sigma x square is 1. Sigma y square is 4. Covariance of x comma y is 1, right? So here, if I substitute here, rho xy equal to formula for rho is cxy or covariance of x comma y by sigma x sigma y. That is 1 by 1 into 2 or 1 by 2 rho value. And directly if I substitute in the equation, what is the equation here? So we know the definition of density function: 1 by 2 pi sigma x sigma y under root 1 minus rho square. In the place of rho I have 1 by 2. In the place of sigma y I have 2. As sigma y square equal to 4, sigma y is 2. Sigma x square equal to 1, therefore sigma x equal to 1 into e power minus 1 by 2 into 1 minus rho square. I'm substituting the rho here. X minus x bar here, x bar is 0. Y minus y bar here, y bar is 0. Right? Here also x minus x bar, y minus y bar. Right? Here I have rho here. So here also it is rho is 1 by 2. Right? By substituting all the values, I'm able to write this equation. By simplifying this, the simple calculation, how do you write the density function? The density function is 1 by 2 into here. What is this? Under root 1 minus 1 by 4, root of 3 by 4. It becomes root 3 by 2. 2 gets cancelled. 2 root 3 5. Root 2 root 3 pi. E power. After simplification, I can write the expression like this: minus 2 by 3 into x square minus xy by 2 plus y square by 4. So this is the way to derive the density functions or jointly Gaussian density functions by knowing the parameter values, statistical parameter values, right? So far we have discussed two random variable case. Let us move on to n random variable case. How do you write for n random variable? Similar to the two random variable, n Gaussian random variables x1, x2 to xn are said to be jointly Gaussian if their joint density function can be written as like this. So here, the jointly Gaussian density function for n random variable case can be represented like this. What is this Cx here? It is a matrix of covariances. It is called covariance matrix. Cx inverse, mod Cx inverse power 1 by 2 by 2 pi power n by 2 exponential of minus of x minus x bar transpose. It is transpose Cx inverse x minus x bar by 2. What is that Cx? What is that x minus x bar in the multiple random variable or n random variable case? Here, x minus x bar is a matrix. It is a column matrix which is having the elements as x1 minus x1 bar to xn minus xn bar. Similarly, here Cx is a covariance matrix, that is C11, C12, C1n up to Cn. That is C11 is nothing but covariance of x1 and x1. C12 is covariance of x1 and x2. In fact, covariance of x1 and x1 becomes variance, right? So all these diagonal elements becomes variance. All these diagonal elements will become variance, and the remaining terms will be the covariances of the elements, I mean individual random variables, right? And here what is Cij? In fact, C11, C12, like that I am writing. The general term I can write here, Cij is nothing but covariance equal to expectation of xi minus xi bar into xj minus xj bar, where the whole term equal to variance if at all, if yi equal to j. Just now I said all the diagonal elements, C11, C12, C22, C33, if at all, if the terms I and j are equal, ultimately it becomes variance. If not equal, it will be covariance itself, right? For example, two random variables, general expression can be taken like this. Example, diagonal elements are that is variances of random variables, and here it is, this is covariance, this is covariance. Am I clear? Yes. The joint Gaussian density in n random variable case is also called as n-variate Gaussian density. Joint, that is, for two random variable case, the joint density function is called bivariate. Here, for n random variables, the jointly Gaussian density function is called n-variate Gaussian density, right? So now, another important topic is, here we have discussed two random variable case and n random variable case. Just let us try how to derive the two random variable jointly Gaussian density function from the n random variable jointly Gaussian density function. And sometimes in the examinations, they are asking these type of questions, right? So here, how do you derive? Simple thing, you need to substitute like this. You need to substitute the values of covariance, that is Cx, and value of x minus x bar transpose, and value of Cx mod Cx inverse whole power 1 by 2, like that, right? So for example, we know that for the n random variables x1 to xn, the joint density function can be represented like this: mod Cx inverse whole power 1 by 2 here, right? Like by 2 pi power n by 2 into exponential of minus of x minus x bar whole transpose Cx inverse x minus x bar by 2. Now we are just taking only two random variables. So therefore, can I write the x minus x bar like this: x1 minus x1 bar, x2 minus x2 bar. It is a column matrix with two elements. Similarly, transpose in the sense that is the row column matrix becomes row matrix, or row vector, I can say. So x minus x bar whole transpose is equal to x1 minus x1 bar, x2 minus x2 bar, right? And Cx covariance is what? Just now we have taken this particular expression in the previous slide. Covariance equal to, in fact, it is C11, C12, C21, C22. C11 is variance of x1, C22 is variance of x2, C12 is covariance of x1 and x2. Similarly, C21 is also covariance of x2 and x1. Both are equal, in fact, right? So here, if I take, if I substitute these in the above expression, before substitution, we need to calculate some more terms. Cx is known, but we are supposed to calculate inverse of Cx, that is Cx inverse. How to find the inverse of the matrix? Inverse of the matrix, 2 by 2 matrix. First, we need to find the determinant, that is 1 by AD minus BC into, we know the formula, 1 by AD minus BC into D minus B minus C A. We know the formula for this, inverse of the matrix, 1 by AD minus BC into D minus B minus C A. I'm just writing the same way. Yes. Therefore, mod Cx inverse becomes what? 1 by sigma x square, sigma x1 square, sigma x2 square, 1 minus rho square. To avoid the confusion, I'm just taking, instead of x1 and x2, I'm taking x and y for better understanding, right? And substitution of the above expressions in the density function of n random variables, we can get the density function of 2 random variables, absolutely. And at the same time, let us replace x1 and x2 with x and y for better understanding to avoid the confusion, right? So therefore here, if I substitute it, x minus x bar transpose is x minus x bar, y minus y bar. Cx inverse is already calculated. X minus x bar is, here it is row matrix, it is column matrix. That is x minus x bar, y minus y bar, right? So if you observe here, x1, x2 are replaced by y and x and y, right? So now I can simplify this. That is, I can just take the matrix multiplication. Matrix multiplication. This is the row, that is row matrix 1 by 2. This is 2 by 2. The product of these two will be again 1 by 2. 1 by 2 and 2 by 1 matrix. The resultant will be 1 by 1 matrix are a single element. So therefore here the resultant will be like this. Just you can apply the simple matrix multiplication and you can get this, right? So here finally we can write the density function like this after calculating all the, after simplifying all the equation. So all the equations, the whole expression can be rewrite like this, right? So finally we're able to derive the jointly Gaussian density function of two random variables x and y, right? This is the way to derive the two random variable jointly Gaussian density function from n random variable jointly Gaussian density function, right? Now let us see the properties of the jointly Gaussian random variables. Coming to the first property, x and y are jointly Gaussian, then x and y both are Gaussian. That is, if at all if the two random variables are jointly Gaussian, ultimately individually also they are Gaussian. But here the reverse is not valid. In the sense, vice versa is not applicable. See there, the converse of the above result is not true. That is, if each of x and y is Gaussian and x and y are not necessarily jointly Gaussian. That is, if the random variables are jointly Gaussian, their individual density functions are ultimately Gaussian. But if at all if the two individual random variables are Gaussian, their joint density function need not be Gaussian or jointly Gaussian, right? And Gaussian random variables are completely defined through only their first and second order moments. Gaussian random variables. That is, just now we have seen the definitions. First and second order moments. That is using only mean values and variance values. We are defining the density functions using only mean and variance. We are not taking the help of third order moments like skew and all, right? That is by their means and variances and covariance, right? If x and y are jointly Gaussian, then for any constants a and b, the random variable z, that is given by z equal to ax plus by, is Gaussian, with the mean z bar equal to ax bar plus by bar and the variance equal to a square sigma x square plus b square sigma y square plus 2ab into sigma x sigma y rho xy. That is, it can also be proved. In fact, it can also be proved, but here you need to remember that if at all if the two random variables are jointly Gaussian, then ultimately the linear sum of it, the linear sum of the random variable which is derived by the linear sum of random variables is also a Gaussian with the given mean and variance like this, right? The next property is, if random variables are uncorrelated, they are also statistically independent. We have also seen this. If they are uncorrelated, they are statistically independent. Why? Because if they are uncorrelated, fxy equal to fx into fy. The same is valid for statistical independence, right? The random variables produced by a linear transformation of x1 to xn will also be Gaussian. Let us see more about linear transformation of multiple random variables in the coming topics. For time being, you just remember this. If at all, if I produce any new random variable by taking the linear transformation of the existing random variables x1 to xn, the resultant will also be Gaussian. We also see the proof for this in the further topics. Just remember the property. And any k-dimensional marginal density function by integrating out n minus k random variables will be Gaussian. I repeat, any k-dimensional marginal density function. K-dimensional marginal density function. Here, how do you get the k-dimensional marginal density function? Only by integrating out n minus k random variables. That is also the k-dimensional marginal density also Gaussian, right? And the conditional density function is also Gaussian. If at all, if the random variables are taken x1 to xn are Gaussian, their conditional density also Gaussian. And all the marginal density functions derived from n-variate Gaussian density function are Gaussian. From the n-variate Gaussian functions, if I derive individual density functions, absolutely they are all Gaussian. Why? Because we have seen the very first property, that is in the jointly Gaussian random variables, that is if at all if x and y are jointly Gaussian, x and y individually also Gaussian. Here I am saying that if x1 to xn are jointly Gaussian, individually all the individual random variables are also Gaussian. Simple property. And all the conditional density functions are also Gaussian, right? So here there are the properties of Gaussian density functions, right? So in this class we have discussed about joint characteristic function, how to derive the joint moments from the joint characteristic function, and what is jointly Gaussian random variables, and how to define the jointly Gaussian density function in the case of two random variable case, and also in the case of n random variable case, and how to derive the two-dimensional or the bivariate Gaussian density function from the n-variate Gaussian density function. In the next session, we are going to see the transformations on multiple random variables. Thank you.